Okay, we're going to try to explain probability with three different things. In the last lesson, I used a die. In this lesson, I'm going to use a dartboard, and in the third lesson, I'm going to use a spinner. So any of these things can be used to kind of get the idea. We're not going to flip coins in this particular set of lessons, but that's the one that's used as well. So think of this as being a big dartboard. Use D for dartboard. And assume that every time you throw a dart, you're always going to land somewhere on the dartboard. So the probability of hitting the dartboard is 1. Okay? You're always going to hit the dartboard. And then we'll also assume that the probability of landing on any point in this dartboard, they're all equal. So the probability of landing, no matter what spot you are, they're all the same. And so I don't think I have the numbers, the sizes quite to scale, but they're close. So the probability of landing inside A is this outside circle here. The probability of landing in A is 3/4, is 3/4. The probability of landing in B, right there, is 1/4. And then the probability of landing in this particular little spot inside there, C, is 1/8. Okay, so just assume that those probabilities hold. Okay, and here's some questions I want to ask. What's the probability of landing in A and C? And I'm going to use this symbol again. I could use the word and, but mathematically that means the same thing. Of landing in A and C. Do you agree that those two things are mutually exclusive? If you've landed in A, you're not in C. If you landed in C, you're not in A. So they are mutually exclusive. The probability is 0. Okay? What's the probability of landing in B and C? That's also going to be 0. Agreed? And finally, what's the probability of landing in A and in B? Okay? What's the probability of landing in A and in B? Well, to land in A and in B just means you've landed right in there, right? And the probability of landing in there, which means you're also in A, that's going to be 1/4. Agreed? Okay. What's the probability of landing in A or C? What's the probability of landing in A or C? Well, these two things are, again, mutually exclusive. So it's the probability of this together with the probability of this. So it's going to be 3/4 plus 1/8, which is 6/8 plus 1 is 7/8. Agreed? The probability of B or C is going to be, these are mutually exclusive, so it's going to be 1/4 plus 1/8, which is going to be 2/8 plus 1 is going to be 3/8. And then the last one, what's the probability of A or B? Well, you're in A or B as long as you're in A, right? So as long as you're in A or B, and that's everything right there. So that's going to be 3/4. Okay, are you good? So that's kind of a review of last time. Let's do one other thing to review. What's the probability of the complement of C? Remember, the complement means that you did not land in C. Since the probability of landing in C is 1/8, it's going to be 1 minus 1/8, which is going to be 7/8. Okay? And I guess as long as I'm doing them, what's the probability that you did not land in A? That would be 1 minus 1 3/4, which would be 1/4. The probability that you did not land in B, well, the probability of landing in B is 1/4, so the probability of not landing in B would be 1 minus 1/4 is 3/4. Okay? Good. Okay, now that was all review. Here's the new idea. What's the probability that you are in A given that you already know that you're in B? Okay, what's the probability that you're in A given the fact that you already know you're in B? So it's like if you put a blindfold over your eyes and you know what the board looks like and you threw it at the dartboard and you want to know whether you're in A or not, and I say, well, I'll give you one hint. You're in B. Well, if you're in B, then are you in A? Yeah, you know for sure that you are, right? So the probability is 1. Okay, the probability is 1. Now, let's compare that to this one. What's the probability that you're in B given the fact that I tell you that you're in A? Okay, think about this one now. If I just asked you, if you had a, we said this was 1. If you had a blindfold over your eyes and you just threw it at the board, and I didn't tell you anything, and I asked what are the chances that you're in B, you'd say, well, the chances of landing in B would be 1/4. Agreed? If that's all you knew. All you knew is you hit the dartboard, and so you'd say 1/4. But now I say, hey, wait a second. I'm going to give you a hint. You landed in A. Okay? Well, as soon as I tell you that you landed in A, now you've got a better chance of landing in B. Agreed? Because that means all this stuff is no longer even a possibility. The only thing that's a possibility is this stuff. So it's kind of like A is your new dartboard. You know that you're in A, and given the fact that you know that you're in A, what are the chances that you're in B? So if you think about it, you say, well, the chances of A are 3/4. That's the chance you're in A, and the chance that you're in B is 1/4. So 1/4 divided by 3/4 is 1/3. So given the fact that you know you're in A, now B takes up 1/3 of A, and so now the chances of being in B is going to be 1/3 because you already know you're there. Okay? So let's see if we can get a formula that gives us the idea that we're talking about. To say the probability of B given A is to say, what's the probability that you're in both A and B? Okay, because after all, we want to know that we're in B. So what's the probability that you're in both of them divided by the fact that you already know you're in A? That's called the probability of B given A. And similarly here, this is going to be the probability of A and B divided by, this is your world, divided by the probability of B. Okay, so let's see what these numbers come out to. The probability of A and B, what did we say that was? Probability of A and B, that's A and B. Right there, it's going to be is 1/4. Yeah, that's just this. So that's going to be 1/4 on top. The probability of B is 1/4. 1/4 divided by 1/4, sure enough, that's 1. If you do this one, you say what? You want the probability that they both happened, which means you're in both of them. That's 1/4. You divide that by the probability of A. Probability of A is 3/4. And so 1/4 divided by 3/4, remember how you deal with rational numbers? You flip it over and multiply. You can cancel those and you get 1/3. That's going to be 1/3. Okay? So that's the idea. That's the idea. Let's do one more. What's the probability that you are in A given the fact that you know you're in C? Well, if you know you're in C, what are the chances you're in A? It better be 0, right? Let's check it out. It's the probability of both of them happening divided by the probability of the bottom one, and the probability of A and C is 0. 0 over 1/8 is 0, sure enough. Okay? So that's called, the words for this is the probability of B given the fact that you know that A is true. Okay? That's called conditional probability. Conditional probability. It's the probability of one thing on the condition that you know that something else happened. Okay, so let's do another example, another set with a different A, B, and C. Or maybe I think we'll just choose A and B this time. Okay, here's my diagram. A is going to look like this. And B is going to look like this. Okay, so now the problem, we don't have any C anymore. So I can get rid of, let's just kind of start over as we go. So the probability of A, of being in A, is now going to be 1/2. And the probability of being in B is now going to be 1/3. And this intersection, so here you have 1/2 here, you have 1/3 is all that, and then this part in the middle, we're going to say is of A, let's see, I guess we might as well start over again. And and the probability of B is 1/3, and we'll also say that the probability of A and B is equal to 1/12. Okay, so that's going to be 1/12 right there, 1/12. Okay, that intersection is 1/12. Okay, are you with me? Okay, so that's what we know. And so we want to find, as before, we want to find the probability of A given B. Okay, what's the probability of A given B? So, what does that mean? That means that we want to know what's the probability that you are in A given the fact that you know you're in B. In other words, again, you close your eyes, you throw a dart on the dartboard, and if you don't know anything and I say what's the probability that you're in A, you would say the probability is 1/2, because that's half of the area of the board, and so you'd say the probability would be 1/2. But now I tell you, you landed in B. You landed in B, so how does that change things? How does that change things? So you know you're in here someplace. See that? You're in here someplace, and given that this is your world, you know you're in there, what are the chances that you're also in A? Do you see what you want? So you want, what's the probability that you're in both of them? Because you're given the fact that you're in B, and you want to know the probability you're in A. So you're in both. You want to know what's the probability I'm in both of them, given the fact that I already know that I'm somewhere in here. So let's calculate it. It's going to be 1/12 divided by 1/3. And again, if you flip it up and multiply, you get 1/4. You get 1/4. So in other words, if I tell you that you're in B, then since there's a total area of this is 1/3 and the total area of this is 1/12, 1/12 divided by 1/3, which is the whole thing, is 1/4, and so that would be your conditional probability. Okay, let's do the other one. What's the probability that you're in B, given the fact that I've already told you that you're in A? Well, we'll do it the same way. Again, we want to know the probability that you're in both of them. That you're in here. What's the probability that you're in here? Because we're assuming you're in A, and now we also want to assume that we've hit it. What's the probability you're in B? So that would be that you're in both of them. But what's your whole world? We're assuming that we know already that you're in A. So we know you're in here. So it's going to be this over this. This is your world. And so it's going to be 1/12 divided by 1/2, which is 1/6. Okay? So there you have those. Remember what those are called? Conditional probabilities. Okay. Now, I've got one more important definition to give you. A is independent of B. A is independent of B. I'm going to give you a couple different definitions. If B has no effect on A. In other words, A is independent of B if knowing B tells you nothing at all about whether A occurred. Okay? For example, the color of my shirt is red. Okay? The color of the shirt that you happen to be wearing has nothing to do with this color. Well, I shouldn't say that. You might be wearing a Davenport color as well. So actually, this is an example where maybe the two do have something to do with each other, okay? So you might also, if you're a Davenport student, be also wearing a Davenport shirt. And if you are, then it might be a red shirt. So those two things are slightly dependent. They're not independent, okay? It's knowing that I'm wearing a red shirt, knowing that you're a Davenport student, you might also be. So knowing something about Davenport's colors tells us something about the shirt you might also be wearing, okay? So actually those are not independent. So let's choose one that is. The fact that I happen to have a shirt with a little round circle here in the middle has nothing to do at all with whether you are wearing glasses or not. Do you agree with that? Nothing at all with whether you're wearing glasses. So knowing that I have a circle, a shirt with a circle, if I told you that, that tells me nothing about whether you're wearing glasses. If you're wearing glasses, that tells me nothing about whether I happen to have a shirt with a circle in it. So those two things are independent of each other. Okay? What's another example? The weather today versus the weather yesterday. Are they independent or not? No. If you knew that the weather yesterday was 90 degrees as it was, that tells you that more than likely the weather today is not going to be 10 degrees, right? Not at all likely. So those two things depend on each other, okay? It doesn't mean you know exactly what it is, but they depend on each other. They have an effect on each other. Knowing one is going to give you some knowledge about the other. But knowing what the weather is right now in Holland, Michigan today, what does that have to do with the weather on Antarctica 2,000 years ago? Those two things have nothing to do with each other, okay? They would be totally independent. One doesn't give you any information about the other, and so that's what it means to be independent. That knowing about one gives you no knowledge about the other. So after I explain that a little bit, then it should make sense what I'm going to write down as the mathematical definition. The mathematical definition is that the probability of A given B is exactly the same as the probability of A. Okay? knowing about B gives you no information at all about A. Those two things are the same. That's what it means for A to be independent of B. Okay, make sense? That's what it means, that knowing about B gives you no new information about A. Here it did, right? The probability of A all by itself was 1/2. But when I told you something about B, then it changed it to 1/4. So it changed it. But if those two are the same, then knowing one has no effect on the other. Those two things are said to be independent. Okay. So let's see some things that are true if this is the case. And here's the theorem. If A is independent of B, that means, as I just said, that the probability of A given B is equal to the probability of A. We know that. Period. Also, what's the definition of this? The definition of this is that the probability of A given B, it's always the case that this is going to be true. Okay? So look at here. This thing is equal to this, and this thing is also equal to this. I'm going to make this a squiggly line just so you don't think there's any dividing happening there. Okay? So this is equal to that, and it's also equal to this. So, since this thing is equal to both of them, what do I have? I have the probability of A is equal to the probability of A intersect B divided by the probability of B. See that? These two things are both equal to this, so they're equal to each other. And now I can multiply through, and if I multiply through by the denominator here, I get that the probability of A intersect B is equal to the probability of A times the probability of B. Okay? So if A is independent of B, here's one nice fact I know. I know that the probability of the intersection is just the product of the probabilities. That's one nice thing I know. Here's another nice thing I know also, let me make sure I read it correctly because I have it down here nice. Also, the probability of B given A is equal to, well, what's the definition of the probability of B given A? There it is right there. It's the probability of A and B divided by the probability of B. But now, since A is independent of B, I know that this thing right here is equal to this. So this is equal to the probability of A times the probability of B, all divided by the probability of B. Okay? This probability of the intersection is equal to this product. And now notice what I can do. Oh, my mistake. Did you catch it? It's trying to do this without any mistakes. The probability of B given A is what? It's the probability of the intersection divided by the universe. What's the universe? What's the whole universe? That's probability of A, okay? This should have been a probability of A. And now what can you do? Now you can divide this out with this, and you get the probability of B. So look at here. Look at here. If A is independent of B, that means that knowing B tells me nothing about A. And here's what we've just proved. We've proved that if knowing B tells me nothing about A, that this probability is the same as this, then what's also true about the effect of A on B? Knowing something about A tells me nothing about B. See that? Knowing this, knowing something about A, tells me nothing about B, and so that means that B is independent of A. And so what did we conclude? If A is independent of B, then B is independent of A, and so we just sometimes say A and B are independent of each other. Okay, if one is independent of the other, if knowing what the weather is here tells me nothing about the weather at Antarctica, then the weather on Antarctica isn't going to tell me anything about the weather here. Okay, if one has no effect on the other, then the other has no effect on the one. Okay, and so that's what it means to be independent. And the key is that if two things are independent, then this is also the case. This is also true. Okay, so I'm gonna get rid of all of this stuff now, and just write down the key result in shorthand, so I have some room. A and B independent. What does that mean? It means that the probability of A given B is just the same as the probability of A. Then we also know that the other one is also true. The probability of B given A is just the probability of B. This tells you nothing about A. This tells you nothing about B. And also, this is the easiest one to apply. The probability of them both happening is just the product of the probabilities. Okay? So, let's go back to this problem. If I wanted this A and this B to be independent, then what would this have to be right here? Let's check it out. What would this intersection have to be? The intersection would have to be equal to the probability of A times the probability of B. What is the probability of A? It's 1/2. What's the probability of B? 1/3. 1/2 times 1/3 is 1/6. So to be independent, this probability here, instead of being 1/12, would have to be 1/6. Oops, 1/6. 1/6. So let's change it to 1/6. And now let's see if these things actually hold. Okay, let's see if they hold. If this is 1/6, let's see if these holds. Okay, let's check them out. The probability of A given B now is what? It's going to be 1/6 divided by 1/3. 1/6 over 1/3 is 1/2. Okay? What's the probability of B given A? This is going to be 1/6. 1/6 over 1/2 is 1/3. Is it the case that the probability of A given B is just the probability of A? Sure enough. See that? The probability of A given B is equal to the probability of A. They're both equal to 1/2. Is it the case that the probability of B given A is just the probability of B? That this thing tells you nothing at all? Well, are they both equal to the same thing? Let's check it out. They're both equal to 1/3. Yep, there you go. So if the dartboard looked like this, and you had your blindfold on, and you just threw it, and I said to you, what's the chances that you landed in A? You would say, well, chances that I landed in A would be 1/2. And I'm going to say, well, I'm going to give you some new information. What are the chances that you landed in A? I'm going to tell you though that you landed in B. And if you landed in B, how does that help you out? And so you know you landed in B, and so you know you're in here. You know you're in here, and given that you're in here, what are the chances that you're in A? Well, this whole thing is 1/3. This part right there is 1/6. So I told you you landed in B, so you know you're in this world, and you want to know what are the chances that I'm also in here. 1/6 divided by 1/3 is also 1/2. See? So by me giving you that extra information, it didn't help you out at all. Those two things are independent of each other. Okay, lots of good stuff here. Lots of good stuff. Finally, let me say two things. People often get two things confused. They get the idea of being mutually exclusive and being independent. You get those two things confused. They're totally different though. To be mutually exclusive means that two things cannot happen at the same time. If they can't happen at the same time, then if I tell you that you're in here, you know for sure that you're not in there. These two things are very dependent, right? If I tell you you're in here, you know you're not in there. And so they are dependent, and so remember, to be mutually exclusive means that the probability of A intersect B is 0. They can't both happen. To be independent means that you do have some stuff in the overlap. See that? You do have some stuff. What's true about probability of A intersect B? It's not 0. It's equal to that. Okay? That's what it means to be independent. Okay? So to be mutually exclusive, to be independent of your parents means you just do whatever you want, no matter what your parents tell you to do. That's what it means to be independent. To be mutually exclusive would be to say, hey, if they say to you, go to the movie, then for sure you're not going to go to the movie because you're not going to do what they say. Whereas maybe you wanted to go to the movie. So to be independent is to say, oh, you told me to go to the movie? I don't know. Whatever my friends decide to do, that's what we're going to do. Maybe we'll go to the movie, maybe we won't. Who knows? But there's going to be some intersection there. But to be mutually exclusive is to say, nope, if they tell you to do it, you for sure are not going to do it. So your behavior is changed by what they've told you. See that? It's restricted by what they've told you. Okay, very good. So, last thing I want to do is another kind of interesting problem, which fits very well with our present time of 2020, where we have the COVID-19 going on. Suppose you're in a town, you have the coronavirus. Suppose you're in a town with 10,000 people, okay? And 1% of these people have a virus, have some sort of a virus, and it's undetectable unless you take a test. Otherwise, they don't know that they have it. Okay? 1% have a virus. And the test is 99% accurate. Okay? Which means that if you actually do have the virus, there's a 99% chance that it'll tell you you have the virus, and if you don't have the virus, there's a 99% chance that it'll tell you that you don't. Okay? It's true, it's accurate 99% of the time. And the question is, you go in to get tested, and the answer comes back, it says check mark that you have the virus. Okay, that's what the test says. And given the fact that you know this to be the case and you know this to be the case, if you get a check mark that you have the virus, how concerned should you be? Okay? Does that mean it's very, very likely that you have it? Does it mean it's almost sure that you have it? Make sure that I'm still recording here. Okay, very good. Does it mean it's almost sure? What does your intuition tell you? Okay, let's check it out. So first of all, here's a town of 10,000 people. Since 99% of them do not have the virus, that's 9,900 of them no virus, and there's 100 of them, 1%, which do have the virus. Okay, so these people do not have the virus. These people have the virus. There's your 1%. 100 out of 10,000 is 1%. Okay. So let's think about this. All these 10,000 people go in for the test. Okay? All these 10,000 people go in. Of these 100 people that go in that have the virus, it's 99% accurate. So it's going to say that 99 of them, I'll put a circle around it to mean that that's how many people the test says have the virus. Okay, it's 99% accurate, so out of those 100, it's going to claim 99. Out of these 9,900 which don't have the virus, it's 99% accurate, which means 1% wrong, and 1% of this, if you take this times 0.01, you get 99 again. So now you have 198 people in the room, all of whom the test has said, you have the virus. And of those 198 people, 99 of them actually do, and 99 of them actually don't. So the chances that you have the virus, given the fact that it detected it, is 1/2. Just 1/2. Isn't that interesting? So there's another example of how understanding probabilities and being able to work with them can help you see things that otherwise kind of defy your intuition. Okay? So it's an important example of how studying and mathematics and studying probability can help you understand the world a little bit better. Okay, very good.